Hey there, everybody. Today we're going to look at positive and negative work. Just a heads up, it's got its ups and downs. Just kidding. That's it's a physics joke slash dad joke slash pun, maybe. Just dad joke, I guess. Anyways, maybe you'll laugh at it later. Work done while lifting or lowering things. I should say lowering there instead of falling. But anyways, things can fall and have work done on them too by gravity, right? And then also gravitational potential energy. So a key idea that I want to make sure is obvious here is that when you're doing work, it's a transfer of energy or a change of energy, right? And so quite often the work energy theorem idea is just that we're going to pay attention to the kind of energy that work done ends up as. So you do some work on something and it ends up with gravitational potential energy, or later on it'll end up as kinetic energy, or whatever. So that's the idea of the work energy theorem. I'll point that out when we see it in action. All right. So positive and negative work can be a kind of a confusing thing, but certainly when you do work on something, you change its energy, right? And so if you look at the final energy and the initial energy, if you look at the change by doing final minus initial, if we have a positive work case, then the initial would have been the smaller one. The final ends up being the bigger one, right? So the energy of the system is increasing. In a negative work case, we've got the final one being the smaller one, the initial one having been bigger. Okay, so the energy of the system is decreasing. So if you are lifting an object, obviously you're increasing the gravitational potential energy, and we'll see that in action in the lesson. And if you're lowering an object, you're decreasing the gravitational potential energy. I'll stick with that one. We'll do the kinetic energy version later on. It involves acceleration, which we already know a ton about. So it's all coming together. So here's a little GIF along the side here of someone doing work. If you are lifting if you're lifting the thing, I don't know where the rest of her weights went, but anyways, if you're lifting, then you've got an applied force, right? And you've got this lift, or the displacement in the positive direction as well. So basically you'd have your, let's say, work. That says work, sort of. Work done would be your delta E equals F delta D. And, and looking at this, they're both up, right? You've got an applied force up, and you've got a delta H up as well, right? So they're both positive, and so we have positive work being done. And then in a lowering case, then we got to switch this around. I didn't switch my arrow yet. Do that easily enough, though. Ungroup things here, and I will just finish ungrouping that and move that sucker around. So now we are lowering, right? Well, the thing is that the applied force is still in the upward direction. When you're doing this and you're working out, you're still putting an upward force, and you're lowering with a slow constant velocity. In order to do that, you would need to have the acceleration in the y direction be 0, which means your F net in the y direction needs to be 0, which means you've got 0 equals the applied force plus the gravity force. And so you end up with your applied force being the opposite of the gravity force, right? By subtracting both sides, right? Subtracting the gravity from the both sides, right? So you've got this applied force. I could have done that same analysis on this page as well. I just didn't think of it because it just seemed too obvious, right? But basically, that's going to link to this idea later on about the gravitational potential energy, the idea that Fa is equal to negative of Fg and so on, okay? So it's just really nothing different. That equation, when we get to it, is nothing different than this actual work equation. It's just tailored specifically to a gravity lifting and lowering kind of case. So same deal here. We've got work done, and we've got our delta E equals our F delta D. And of course, we've got our Fa is still up, but our delta H is down, right? So pretty easy to tell here that you're going to have a positive number and a negative number. And so you're going to have a negative work done. Okay, so we've got a positive work done and a negative work done in these cases, right? So when you're working out, if you're exercising, physiotherapists, whatever you call them, people helping you with proper technique and working out, exercise therapists or whatever, fitness trainers would tell you go slow on the way up and slow on the way down, because slow on the way down is actually part of the workout, right? So you're adding energy to the system and then slowly taking it out, and your body's working that whole time. So this page isn't much different, but I'll just go through it as well, just as a review of it, right? So we end up with this positive. I think I meant for those to be revealed later on, actually, but same deal, right? We've got this constant velocity stuff, and so actually this page is no different at all, is it? I'll just reveal it. All right, just worked on the fly there instead of revealing, but same result, right? So yeah, we have our positive work kind of case and our negative work kind of case. All right, hopefully that's working for you. This slipped out, sorry. So when you look at work done and we're looking at the energy transferred, and when you have a constant velocity lift situation, this is what I did on the other page there already, just to be, to show it specifically again here. We've got our applied force and our gravity force have to add to 0, and so we get that our applied force equals our negative Fg, right? So if you're looking at a gravity force situation where you're working against gravity or with gravity and so on, this is specific to this kind of situation, and so our work done ends up being the gravity force, or obviously mass times gravity, Fg equals mg from previous work, right? So we end up with this formula. If you're looking at, I'm trying to decide how I want to talk about negatives here. Basically, I prefer what I did already in terms of discussion of negatives. People like to show that the two negatives kind of cancel out here. Actually, this is just, the negative of a negative, right? The Fg, F8. This is negative Fg, which is negative of mass times negative 9.8. So we end up with positive 9.8. So I don't need to worry about that too much. That's just basically what we've already said, right? Anyways, so our change in our gravitational potential energy, just this kind of helps us visualize the idea of like how that energy ends up, right? Ends up as this gravitational potential energy quantity, right? That's our change in the gravitational potential energy. This idea of work and, is a change in energy itself, right? This is, delta E, right? That's what W really is. I normally write it like that. Becomes the change in gravitational. Really, that is the work energy theorem that I was mentioning earlier, right? Work done becomes this, the delta E that you do work on the system becomes that delta E in that new form of energy. So we've got the delta Eg is really equal to the delta E as well, right? So this was equal to the delta E in the first place, right? So delta E becomes delta Eg, right? The change in energy in the result. If you are starting from 0, basically, if the initial gravitational energy is 0, then delta Eg is just equal to Eg, right? Meaning if you had, so we have delta Eg. Let me just do that for you. Delta Eg equals Eg final minus Eg initial, right? If we make this be 0 at the start, so you're at the bottom, you have you think of yourself as having 0 gravitational potential energy relative to like the floor you're standing on, right? Or the chair you're sitting on. So gravitational potential energies can be taken relative to any location. So you relative to the chair you're sitting on is 0. If you fall off your chair, you'd quickly find out that you had some gravitational potential energy relative to the floor, right? But oftentimes, I'm just trying to justify there that oftentimes you'll just see Eg equals mg delta H. And this is basically just Eg relative to starting point, right? Relative to a 0 starting point or reference point. Okay, so quite often the delta is left out on that one. I kind of think it shouldn't be, but it's not up to me necessarily. yeah, so if, just number example here, if you have a 2 kilogram object and it's lifted 1.5 meters, how much gravitational potential energy was added to the system. So you're just, oh, that's easy enough. We've got our mg delta h equation, right, which is our 2 times our 9.8 and so on. So that's nice to be able to use that equation directly. Absolutely, though, the same thing as, or, just basically delta E equals F delta D. So you'd be like saying, okay, well, we've got our acceleration, we're just lifting, right? So let's just say lift force equals, for simplicity here, we'll just say the lift force equals Fg. And this is just for constant acceleration or constant motion lift, right? I'll deal with that a little bit more in a second. But I think it's reasonable just to sort of accept that and say that makes sense. And it's actually the negative of it, but basically we end up with a positive value of the, it's a negative of a negative, right? So end result is we just kind of do the same thing, right? We just end up putting in there you could calculate out, I suppose, the gravity force here. So do the 2 times negative 9.8 and then say, okay, well, lift force is equal to the negative of that and so on. So we have the negative of the negative and we end up with our 19.6, right? Anyway, so we end up with the 19.6 times the 1.5, and we end up with that same answer of the 29.4 joules. Okay, so people could have never written down mg delta h for gravitational potential energy, and we'd still be able to do the same work. Man, on fire with my puns apparently today, not on purpose. We'd still be able to accomplish the same tasks. Anyways, yeah, so we'd have that increase of 29 joules still there, 29.4 joules. And same deal here. You've got your, the signs more being dictated by the idea of the overall, this one being positive, this one being positive. And then if we did that same kind of, trying not to use the word work, we did that same, whatever. Where am I going here? Get the eraser. So down here, same deal, right? In this case, you'd have this one be a negative. So let me just get that, make that big idea negative. And that's why we're ending up with a negative answer, right? So it's just not as obvious, I find, in this case. Like if you had this right here, obviously this is a positive and this is a positive. That's why we have a positive answer. And then here, this is a positive and this is a negative. That's why it's a negative answer. I'm trying to make sure that's obvious. And I feel like the mg delta h equation unfortunately hides some of that. So a bit counterproductive maybe in the end, but again, it's not up to me. But I'm just pointing out those lift forces both times are up, right? So a little bit of a closer analysis to do with this idea of, lifting with the lift force just matching the gravity force and so on. The point is we're not trying to speed the thing up, right? So when you're looking at lifting something with a small constant velocity, it's kind of like people hope that you're going to be okay with just ignoring the energy due to motion as part of this. But regardless, to get something moving, you need a net force. So you need to have some acceleration to get it going, even if it's a small constant, a small velocity, right? So if you give it a small velocity, then you're going to maybe do an extra, like, you're going to add like 2 joules for slow or 200 joules for fast, whatever. Either way, you're lifting it. And at the end, picture here, I should add on, by the way, here, that you'd need for either of these, you're going to need more than, so you're going to need more than FA equals FG, right? Right, and then here, when we're slowing down to a stop or to a stop at the top, then up here, you're going to need less than FA equals negative FG. And so really you push more at the beginning, but then less at the end, and it just averages out, is the idea. Okay, so you have some energy due to motion while lifting, but it's so small, you just have a little extra at the beginning and a little less at the end, and it just cancels out. Okay, so that's that's the ideal situation when we're talking about lifting, because you just want it to be as simple as possible. You want to just talk about gravitational potential energy versus this situation, right? I just found a little video of someone doing this where, the person ends up with some EG, of course, at the top. So at the, say the center mass was here and then the center mass was here. So center mass here, center mass here, right? We've got delta H. And so we've got EG equals, the applied force times the delta H and so on. We got this extra gravitational potential energy at the top. But there's also, if you notice, she ends up going off the ground, right? And so there's also some kinetic energy at that top. So there's going to be some delta EG. There's also going to be some, delta EK, which is energy due to motion. So energy due to motion. That's supposed to be a D there originally. So basically, we don't want to have to deal with that because we haven't covered the energy due to motion stuff yet. So just to tackle it one bit at a time and keep things simple, that's what we talk about it as. So these are all just the same thing, just being able to analyze in any of these GIFs that I can find anywhere, GIFs or GIFs, whichever pronunciation you like. Yeah, so you can analyze the idea of positive energy being done or positive work being done and then negative work being done in all sorts of situations. Snoopy's just a machine there. And you gotta just love dogs, right? Like, I don't know why or how this happens, but pretty cute. And another one, same stuff, whatever. This little video on work, just you can check out that video if you want. It's really not anything more than what I've already said. But if you need more, by all means, look at it. This video here, I'll load that one up, I guess, quick here. So Pile Driving Dragon. Pile Driving Dragon. Videos. Pile Driving Dragon. So there was one video that it was obvious the person was like annoyed on their vacation of all the construction going on near their apartment or near their hotel room. But that is a pile driver. And so what's happening is there's some weird stuff going on with delay of sound delay versus light. So you see the puff of smoke and then you hear the hit later on. That's because of the slow speed of light, or fast speed of light and slow speed of sound. But what's going on is the machine is lifting that up and putting a bunch of gravitational potential energy into the system. And then it's letting it go and letting it slam down, right? So there's positive work being done to this thing and then negative work coming out. That energy ends up in this pile, which is a big steel beam that gets driven into the ground to be the support structure for a building. So instead of having a foundation like you have under a house, they just drive beams way into the ground until they just can't go any farther. And so that's your base structure for the building, right? And so this section here, gets lifted up, and so that's a positive delta EG. And then as it goes down, right, you get a negative delta EG, and it ends up really as, that's supposed to say ends. It ends up as EK or delta EK. Eventually, goes into the post that goes into the ground. And so on. That's the idea, just noticing energy transformations and the concepts of energy around you. So in the questions, I've got another one of the graphing ones. And so analyze the work done during the first 2 seconds and the last 2 seconds and overall. And then I want you to tell me which of the questions, 2 to 8 question or questions, if there's more than one that apply. This graph could apply to, some of these questions. That should be pretty easy to do. And this one here is a little bit of a trick question, or it's tricky. It seems to be tricky, but is this positive or negative work based on what we've talked about? Hopefully you can answer that. And yeah, obviously this here is positive work and this is negative work. So there's some questions, I should say, or 1 or 2 or whatever, questions that have a situation where energy is put into the system and then let back out or taken back out or whatever. Otherwise, you should hopefully find those pretty easy to do at this point based on what we've covered. That's the dream anyways, right? All right. I will talk to you later. Thanks for watching.